Hello, everyone. We hope you're doing well and are staying safe. We'd like to welcome you to today's webinar. Dr. Moshe Ben-Talila, who will be conducting the session, has been the manager of VisiMix's customer support for over 14 years. He has both a BSc and an MSc in chemical engineering in the field of reactors design provided by the Technion, which is the Israel Institute of Technology. He was involved for more than 15 years in technological transfer as a pilot plant manager and as a project manager in an API company. In conjunction with this, he has his PhD thesis in the chemistry field provided by the Hebrew University of Jerusalem in Israel. His dissertation describes the application of practical methods for scale-up process in a specific field in the chemical process industry to show its validity to the chemical industry. He was part of the team that wrote a syllabus for a BSc degree program in pharmaceutical engineering, contributing to the relevant studies for the chemical engineering profession. He was a team member of a committee that wrote the program syllabus for the pharmaceutical engineering BSc degree program in Israel for the Azrieli College of Engineering in Jerusalem. During this activity, he programmed and built a complex of student laboratories for process engineering, biotechnology, analytical laboratory, and pharmaceutical technologies. In this college, he is also a lecturer in reactor design and principle of fluid mechanics. In this session, we'll talk about fermentation. To understand the transfer of oxygen to microorganism media and protect them from damage due to shear rate, it's crucial to characterize the fermentation process in the laboratory. In this session, we will discuss process characterization and transferring it to the next production step. During this webinar, please feel free to write any questions in the chat box. We'll try to answer them during the session or afterwards via email. So we hope that you enjoy today's session. And Moshe, the microphone is all yours.
Thank you very much, Marcy, for the introduction, and thank you to come back again to our forum that is happening every 1-2 months frequently, and we'd like to provide to you more information about how mixing can influence process and how we can advise and progress with this very important activity that is mixing in our process. In this forum, we'll talk about fermentation. The main reason is that fermentation is a field that is growing during the last few years because of the biotechnology industry. And so we wanted to provide to you some general seminar about what will be the influence of the mixing in the fermentation process in the context of biotechnology, and to show to you how you can use mixing calculation, of course, the VisiMix software, in order to help during the activities of commercialization of your process, transfer technology, scale up, and even to understand in the lab what is the environment we need to provide to the process to generate good results. What we'll do today is, of course, to speak more about, a little more about VisiMix, what is the company. After that, we will discuss more about the process by itself, fermentation, and after that, we'll come to open the software and show to you how we can operate. If you have any question, of course, please write the question, because we are many people here, and we'll try to answer at the end or during the presentation. And after that, if you'd like to have a specific and tailor-made presentation for your company, we, of course, we're very happy to organize it for you. So VisiMix is a company located in Jerusalem, in Israel. We develop simulation software for mixing in steel vessel, and more. In few days, you will hear about more products that we are delivering now regarding the capability to every people in this field, in the process industry, in the stage that we are transferring our process from lab to production, to take in consideration and to answer the company what is relevant at this stage. That normally is our capability to generate good environment to the process. The software is used in many companies all over the world. The main use is to take in consideration the mixing during the design of a new facility, that it happens from time to time, more frequently when we transfer the process from one side to other side, where the process is existing, and we need to try to understand what will be the best operation of this equipment in our process that is passing to this stage, or to transfer the process from lab to production. That is the more use of the VisiMix in the world, because we are really changing exactly this stage. We know our process and our materials, but we need to consider what will be the environment we're able to generate. So we're able to know what we did in the lab, and we will be able to understand how we will be able to provide the same conditions in the next step. The process was developed in Russia by Professor Braginski and his team. They were in charge to provide the industry in Russia their knowledge about the mixing design after that operation, and in front of the government in Russia to be sure that the answer is correct. It was before the perestroika. After that, they came to Israel, and we transfer all of this knowledge in software, and provide in all over the world the capability to, in a very fast way, understand how we can provide the process what is required in different levels. So summarize this part, this very fast introduction. VisiMix is based in physical models supported by empirical data. We solve the momentum balance to know the velocity of the flow in order to solve in a realistic way. We characterize every momentum component, the momentum balance equation, and we were able, after, to consider this experimental data and change the models and coefficients according to the specific geometry of the operation that is still vessel, we were able to provide not only the velocity of the flow more, but able to provide the gas holdup, the mass transfer coefficient, the drop size, and in other fields, the concentration of any material, or the solid distribution and more. So this is the brief summary. You can see we're working with companies in all over the world in different fields. You can see here some of them. And we have third users of VisiMix that are very known all over the world. Dr. Victor Tiemoveng, that was the mixing expert of Dow Chemical, and he was one of the editors of this book that supported by North American Mixing Forum. This book is giving a good understanding of mixing into the industry. Okay. We have many customers in all over the world, and the way that we are working with you is after we meet you and provide you some specific presentation about the use of the software and some data that you can provide. We provide to you a starting point quotation that will be more to negotiate together in order to try to start to work and generate enough data that will provide you confidence that it's good for you, and to think how will be the best way to introduce this knowledge into the company through the software to be able to answer in the professional point of view the point that we're discussing about mixing into the industry. Okay, in this seminar, we'll talk about fermentation. And the reason is that it is very known now, and it's one of the main important activities and processes that we are using in order to manufacture materials in different way. And it's very crucial to understand what is the process in one hand and how we're providing the conditions to do the process to progress. So in the process description and how is connecting the fermentation with the process, we'll talk a few minutes about what is the fermentation in the biotechnology industry, how we are able to provide the conditions to this fermentation coming from miscible liquid distribution, because we need to provide nutrients and pH, let's say, that will be in the conditions that this microorganism will be able to grow. We'll talk about, of course, the oxygen transfer from gas phase to liquid phase. This is the main point that normally we were asked during the our first connection with biotechnology company. And we'll touch some points that professional people are aware about, how the microorganism will reproduce itself in equipment that have shear rate, and maybe this shear rate can damage this microorganism. We'll touch about it. Of course, this is more biological question than shear rate. The shear rate, of course, we're able to calculate. We'll explain a little more about it. And of course, after that, open the software and show to you how it's working. So in the biotechnology, the fermentation step is really the first step. We want to have some growth microorganism, and we need to provide the composition of the media through the microorganism withdraw. And this growing of the microorganism is happening in the production fermenter, that so many times from my speech will be named like reactor. And the reason is that normally we're using this kind of equipment. The hardcore was the reactor for the chemical industry. In the biotechnology will be ferment. And after we finish this, we need to do another activities that, of course, the company business can support, how to recover the material, how to purify it, and how to generate our final results. We will discuss today about the upstream. This is the normal name. Upstream is for the fermentation, downstream is for the harvest, purification, filtration, and maybe chromatography. So we can help on both. Now we'll focus ourselves on the fermentation. Fermentation is a metabolic process that produces chemical change in organic substances through the action of enzymes. And in food production, it may more broadly refer to any process in which activities of microorganisms brings about a desirable change to foodstuff or beverage. The main history here and the main difference between the chemical industry and the biotechnology industry is that we are using as a main and important part of our production microorganisms, some live organisms that we use in order to manufacture material. And it does means it is not different from us if we like to get the material that pass through the cell and go outside the cell, this chemical entity we want to get, or something that happened inside the cell and we want to extract after that. For us, the main point here in the fermentation is how we are growing the cell, how we are capabilities to generate a good growing rate that is giving us our microorganism in the best expression. This that we are looking for at this stage. If the material will be inside or outside the cell is a second history. It's more like to know what is the mechanism of the process in the chemical industry. So we like to know what is the mechanism of the process in the microorganism, inside, outside, and what are the products we would like to get. So the first step is to understand what is the fermentation, and in the industry, we need to compound all. We need to organize all, and all the materials that we're using should be utilized well. As you know well, only to remind you, when we talk about microbial growth, we talk about nutrients, fruits, microbial cells will give a cell growth, energy, and reaction products. This is what we're looking for. And we have 4 typical zones of operation. The first one is the starting point, is the lag phase. The second part is the acceleration phase and growing. Normally, we like to control this because here we have a very high change of rate, and we need to control it well. And here the role of the gas transfer, the oxygen to the liquid phase is very important. Otherwise, we have some stationary phase that the rate of the growing and the rate of the deaths in cells are similar. So here we need to think if it is good or not good as to stop the process. And of course, the part of the this phase will be not so desired. So only to give you an idea, we are talking about the like a reaction rate, the growing rate, and the typical reaction rate, growing rate of cells is very similar to Michaelis-Menten's equation for the kinetics growing, and it's taking in consideration some nutrients operation and steady state, and some quantity of growing of cells that we are growing. So it's like a reaction rate for us in the old chemical industry. Regarding reagents and nutrients, I want only to show to you some very fast points. Is that like we have a fast reaction? We need to distribute this material in the tank, and we need to be sure that during the growing of this quantity of cells into the tank, we're able to transfer material. I want to show to you very, very simple way how the material can be dispersed in the tank according to the consumption of this material. And let's think that we are feeding some nutrient. In our case, let's say some group of, we have present there some group of salts. It's like microorganism we have there, and I feed some liquid material. In this case, will be HCl. If I'm spreading well this material, and the microorganisms are using this HCl, okay, they will consume well, and we will not see any change in color. But if we are feeding more than required or less than required, what will happen? We will have some deviation on the concentration in the tank. And we have more videos here. I only will present 2 main videos. What happens when we don't have mixing in our tank? And you see what happens when we don't have mixing. The feeding at every place will be localized one. Okay, you see it's local. This color is local. And we are not spreading well this material all the time. So cells that are in different places will not be able to enjoy with this material. If we are change dramatically the conditions, and now we will use a very fast feeding here in this pipe, fast feeding with high velocity, close to the RP, close to the high velocity of the stirrer here, you will see that we will not have any color. And in between, it can happen anything. For instance, in the middle of the way, we have some plum, close to the impeller at low velocity, we have some color, but it will be well distributed in the tank. And all of this we need to take in consideration, because normally what we are doing, we are doing some tuning of the conditions in the tank by providing some glucose, some material for pH and more. And we need to take care about where we feed in order to spread the material in a good way, and we'll distribute in all the tank. And we have 2 extremes. And it happens in the tank that even if, for instance, I go to a low velocity, and from the top of the tank, you see here, what will happen is that we'll have here around this point where we feed, in a few seconds, you will see a plum of a material entering. It's happening now. You see some color entering inside. And it is a problem. Because when we have this kind of situation, we are doing completely different conditions in the tank, and our microorganism will not feel the same in another place. So we need to take in consideration. Now we reach to the gas liquid mixing and mass transfer. This is the main question that is coming in our desk when we start to discuss with your kind of companies, biotechnology. And here we need to take in consideration that we are discussing about a very typical mass transfer. So mass transfer of material in our case will be the oxygen. The oxygen mass transfer KLA that we are looking for is happening because we have some drive force, that is the deviation or the difference between the concentration, the maximum concentration, the solubility of the oxygen in the liquid phase, that it is the maximum concentration, saturation, minus the concentration we have inside our tank. As you can imagine, that when we are growing the quantity of cells, the concentration in the liquid will go down because we have more material and we are transferring in the same rate. The meaning of this will require more oxygen in order to every one of the cells will be able to use this oxygen and grow. So we are talking about very simple mass transfer. We will able to calculate the KLA. We're able to know what will be the maximum rate, this DCDT, the maximum mass transfer, okay, to the liquid phase, and we will able to connect it with the physical properties. So we are feeding some material. We need to transfer this oxygen from the heat space or from the bottom of the tank to the reactor, okay? And after that, we need to transfer this oxygen into the liquid phase. So this is the primary, this is the liquid phase, this is the gas phase, and it is the secondary drops that maybe are the materials, the microorganism and more, or the nutrients that we feed inside. We have three main distribution of gas. This one, A, is not well distributed, and more than not well distributed, some kind of floating, the material entering and exit. Okay, so we have no using the equipment in order to transfer the gas. We have some no good distribution, but some way that we will be able to calculate for you. And we have a well and good distribution material. We need to find a way to be in between these two stages and try not to be here, because if we are in the A situation, the meaning of this that we're not able to do. All of this the software will provide to you by notification, and after that by number and calculations. For instance, the quantity of gas we will have in the liquid media, is that you have some gaseous drinking, you will see the drops. So we'll be able to calculate the quantity of drops and the capability of the area that we're generating with these drops to transfer the gas to the liquid phase. So this is the work, okay, the way. Once we have the drops, we're able to transfer the gas to the liquid phase, and we have some mechanism that happen here that is taking consideration that our drop maybe is going down. We have distribution of drops, and we need to consider all of it in the place and in average in order to progress. So it is our gas drop and how it's transferring the concentration of the oxygen that we have in the middle of the gas to some film that happen inside the gas into the going to the phase surface, and after that how this material is coming to a liquid phase and disappear or not according to the capability of the microorganism to get this oxygen and to progress. These lines that is coming from the surface to the liquid phase and available to the microorganism can change dramatically in different part of the process, and we need to be aware in order to adjust ourselves and to know what is the capability. Maybe we have more organism than the oxygen we're providing, so we will come to the end of the capabilities to grow and start to death. So we need to have a way and to understand what is the maximum to take in consideration needs as a part of the process. So this is what we explained before that in big place. You see the concentration of oxygen, some mass transfer to the wall, to the interface, and after that we're going down depending on the consumption of this oxygen is coming to some concentration in the liquid bulk or in the liquid film will go down to zero. The meaning of this, we have another way to take in advance. Okay, this is the point. This is the process. I invite you to enter into the website. We have presentations. That this presentation from Dr. Reinaldo Machado from RM2 Technologies that he explained well how to characterize and how to base in the measurement of the gas flow and in the sensitivity to the RPM, he explained how we will be able to take in consideration, in this case it's oxygen, but hydrogen, but it can be oxygen, how we are taking consideration the measurements during the time, how we drop the pressure or we consume with some sensor of oxygen dissolved in the tank, and how to calculate the KLA. It was manually, and after that, how we use the software in order to compare our the experimental results with the VisiMix result, and based on it, the meaning of this, because we have a very good model, we were able to progress and to calculate the expected mass transfer coefficient in the next step. And to summarize and to go, in this case, they went to big equipment from 1 liter to 3,000 gallons with no problem. Okay, this is the main idea. Other example that we have interesting, not in the point of view of characterization, like Dr. Machado showed in his presentation, is a case study that came from company Hovion, and they show us in different point of view. They were in the industry working in aggregation too, because this is the mainly histories we have that we can share. They show us how they went from this equipment to 6,000 to this equipment, and they did all the job exactly that we advise. Go to main important parameters, calculate the shear rate that is available, the drop size, and more. And they wanted to reproduce, because some information they had, because they had another equipment in the production, they continued to work and they wanted to know what was the RPM. So they started with this equipment, H3000, 200 RPM. They succeeded to go to the equipment H6000 with 164 RPM. Long time ago, with the software, they calculate the hydrodynamic parameters that are controlling the gas transfer. And after that, they continue to the equipment H5000, and they wanted to calculate the RPM. The normal way to work, because they had data for it, is to try to understand that the energy of dissipation is very important parameter to keep fixed during the gas liquid media, because it is really generating the capability to diffuse the material to the liquid phase. And they found the conditions in order that will get them the similar maximum energy of dissipation, that is a parameter that is controlling the mass transfer from the liquid to the solid. So they get this solution works very well. And when they came to the H5000 equipment, they continue exactly to do what is expected, calculate again the energy dissipation and found the RPM that will be good for them. But that surprise, the H5000 was 45 less time, more than expected, and very good purity. Very good news, okay? Nobody will take care. If you are so good, you will progress. But these people that were very smart, they wanted to know why. Because even it's so good, it's high, it's not expected, and we need to solve. We need to understand it. It's not expected, something we didn't take in consideration. So they did this job. And when they calculate the parameter that for you will be very, very important, because we talk about microorganisms, and they calculate more the bubble size, the gas voltage, and the mass transfer area or coefficient, they found that it's completely different. You can see in the first two equipment, we talk about very low numbers here. And when we went to the new equipment, we are very good. Here is the point. Now, why? The answer was very simple. Once you have another equipment, you are multiplying the steps that the gas will be inside the tank. And this gives a very high KLA, but only using the third stage. It multiplies by 2 the capability to transfer the gas. So very important for your considerations. The same is gas transfer to the liquid will increase dramatically with some engineering point of view. So I showed to you the scientific point of view, show to you now the industrial point of view. And the final history is that they take the older equipment, HC1000, and increase another impeller, and they got better results too. Okay, so this is the history, the complete history in the point of view of the industry. Okay, very well. So the last point about microorganism. For here, we need to excuse about shear stress and shear rate, and the software is calculating it. I'm showing to you what are the considerations we take in consideration in the models. The first is that in order to calculate the shear rate, okay, we are taking consideration the energy of dissipation, those parameters I explained before that, divided by the viscosity and density. And with some power that is coming from the turbulence theories, okay, this shear rate in the base point of view is coming from the fluctuation of the velocity. And here is the importance to work in the turbulence region. The turbulence region is generating this fluctuation from the average velocity, and it is real the reason that you have some deviations, local deviations in our tank, and these deviations, so this gradient of velocity is generating a local shear rate. This parameter should not be confused with the average velocity gradient, and normally this parameter governs the mass transfer to growing from the dissolution of solids and from the gas transfer. And the point here is that this parameter is higher. You can see here, this parameter must be not confused with the, and its value is typical 1 or 2 orders of magnitude greater than the later. Okay, so taking consideration is the fluctuation of the velocities are the reason for generating this shear rate that can generate the matching the microorganism in one hand, but it's increasing dramatically the mass transfer capability. So those parameters, I of course take this information from our guidance and from our help, and take in consideration because this is an intensive parameter that you can use even in the lab when you identify what is the shear rate that are damaging your microorganism. We of course will be able to be to have this number as a guide for the next step. We, as you know well, more than me, we have different kinds of microorganisms that you can use. Some of the list, and some of them are reported that they're sensitive to the shear rate. Some of them are less reported for the shear rate. From the people that working in the equipment and mass transfer is more likely to know the mechanism of the process. We need to be aware, and if you tell everyone that this can be sensitive, so we'll take care about what is the shear rate and not pass the critical shear rate that can damage the microorganism. Okay, this is all the theory. The last point I want to remind you, because people that know us know that this kind of thinking I am providing, explain you all the way, is try to have some methodology to understand the process. And the main idea is to consider that when we are that when we are working with our process, We are doing some work in the lab, and we will be able to consider all the parameters I explained before that in different point of view in the production step by using the software and calculate. And once you know what are your real capabilities in the production step or in the next step, you will be able to set up an equipment in the small scale that will be similar in the point of view on the environment, the mixing you are generating for your process. Because you bring the mixing from the plant or from the real situation, and you bring your process here at this stage, you are combining between them maybe the first time, and you will be able to understand if the process will run well or not, on how to take care about some deviations we will experiment here. Right, when you finish to do it, you will be able to have final design, and you will be able to have a model that explaining to you how to progress with the software, so with the process. So we have a complete methodology that I will explain to you when you will be part of our customer. We have some publications about it. In the gas liquid system, the main important parameters we need to take in consideration are the circulation flow rate, the energy dissipation, the turbulence shear rate, that all of them will control the gas holdup, the mass transfer area, the drop size, and the mass transfer coefficient. This is exactly the way that we need to think. And from here, we will open the software and show to you how we are able to progress. Okay? We have different products in the company. We'll share with you this presentation, and here you can see a main of the products that we have. Normally, you will work in turbulent. If you are working in laminar, we're able to calculate the shear rate at every step and all, but the efficiency of the transfer will be a little more difficult. If you have more than one impeller in the same stage or an impeller that is off-center, we're able to calculate the same. And if you want to use bubble columns, that normally can happen in this industry, we are able to calculate and to know for without agitator into a tank. And we advise to use scale up, scale out, down, and process evaluation to organize your data and to guide ourselves how to go to scale up, how to keep fix the same gas transfer coefficient. It will be inside the web, inside the software. In the bottom, you will select gas liquid, and you will be able to figure out what happened in any other size. And if you have many options, you will be able to put in one page and to think about your technology transfer. So all the explanation about the products we have, you have here, turbulent, laminar, and more. So take care on it. You can read more, and of course, you are invited to come to our website, and there you will find more information. I want only to the presentation to finalize before I start to show to you the operation of the software, is that come to the software and come to the website and see the models and verification examples. Some of our customers share their experience and testimonials, but I want to emphasize that we're talking about a complete model of mixing into the stirred vessel. It's not only a theoretical solution of mathematical equations, or it is not only some correlations that normally are limited. It's really deeply study, experimental study about friction factors that are characterized in different kinds of flow in the tank for different equipment. We modify the fluid mixing models in order to include this knowledge into the general momentum equation, to characterize every one of them, and to generate the velocity that will be the base in order to calculate other parameters. So we're talking about a complete model and not some pure theoretical or pure empirical. This is our add value to the market. Okay, based on it, I will open the software and show to you how we are able to calculate all the steps, how we are able to introduce the gas to the liquid media, how we're able to know the drop size, and how we're able to transfer this to the liquid media to transfer the oxygen, the material that are miscible there or consumed there, and to show what are the capabilities in the lab and in the production step. We have many questions. I will advise to answer you during the meeting. After that, I will cover these questions. Okay. Okay. So Let's progress. Let's progress now. I will open the software. Software is turbulent. And I will click project new. This is the first step, and give a name that will be lab fermentation, okay? And when we click save, the software asks me, okay, what is your tank? I will use a typical tank in the lab. It's like this. I will not use heat transfer in this stage because normally it's not the main important operation that will change results. And when we click OK, the software asks me about the diameter. Let's say that we have a 1 liter equipment, okay? And I'm using about 800 milliliter in my tank. So it's like this. When we click OK, the software asks me about buffers. Normally in your small fermenter, typical 1 liter equipment that is very available and common in the market, you have buffers like this. You have more sensors, but the buffers are enough because you have 4 normally, and this is fully buffered equipment. And the width of this is normally 10. The length, if I click big number, will be the maximum one. You have some distance from the bottom. Normally you don't have, you have very small distance from the bottom. The distance from the wall will be 5, and the angle it is 0. So you have like this 4. This is a typical fermenter you have in the lab. And when you click OK, normally you are using this turbine, and normally in the lab you have 2 stages. So I will use multi-stage. I will require to have 2. The diameter of this tank normally is about 60, 50, 60, depending. The distance between stage will be, let's say, 50. The diameter of the disc will be 45, and we have normally 6 blades, 90 degrees. The width of the blade will be 12 and 12, the length. Sometimes 10 and 10 it will be okay. The distance from the bottom, the minimum will give me 0, the maximum will be more. This is very big. Maybe I will go to 50, okay? With your permission. You see how fast we can change. And after that, normally you are working about 700, 800, and it is okay. It's good because we have small equipment. We need to provide enough intensity to progress. And maybe the distance from the bottom will be 20, okay, instead of 15. Okay, you see how fast we can change. And the motor power is not so important here in the lab. In the production will be very important because we need to protect our motor. We don't use this parameter in order to calculate nothing. We only use this parameter in order to compare to the mixing power we are calculating and to be sure that your motor will be enough to progress. So we click OK. Now we need the density and the viscosity of the material we have there. I will use water, but I know that you have some deviation from water. It will be okay. This deviation are 10%, 15%. All of them is entering the software with no problem. And I will use Newtonian. If you have a situation that you have non-Newtonian media, you will need to provide a little more data. But in Newtonian media, the point is to provide the viscosity. So I will use 1. Let's say I will use 3 because you have more components there. It's okay. We can have more or less. It is not, we are able to calculate it. Once we click OK, we are ready to start to calculate. What we can calculate? We can calculate many parameters. You can see all the hydrodynamics, all the turbulence, all the mixing times, and of course, if you feed some material, what will be the blending and the concentration of the material in the tank, as explained before that about the color there. And if you have some solids, we're able to calculate the solid distribution, or some liquids for emulsification. It is not here, but it can happen maybe in the downstream. And we can calculate here, as you can see, the estimated dilation from the top or from the bottom, the diameter of the drop, the gas holdup, how much gas we have in the liquid phase, and how much of this liquid phase, the material that we consume or dissolve in the liquid phase, we'll be able to calculate the KLA, and what would be the complete rate. And we have more about heat transfer that is not relevant for here. Okay, so let's only to show to you how fast we can calculate mixing parameters that are important for you. For instance, the shear rate that we discussed before that. Around the impeller is this number, near the buffer is this number, and in the back is this number. Take care about it. these numbers will be very important to keep fixed. After that, if we know that we have some sensitivity of this number in your media and then your microorganism, you see fast, click get solution. If you want to know how long, what will be the circulation flow rate, for instance, you can see immediately here circulation flow rate, what is the cube per second, or what is the, how long it takes one round of all the volume to pass through the equipment. It is very fast in this case, very small equipment. This number can be very important when we are talking about big equipment that the time is longer, and if our material is not so stable and tend to react, maybe we have some impurities that we don't like to have in the process, is depending on the process. What I will focus myself is to feed the data for the liquid, okay? So I will click here in the gas mass transfer rate, and the software will ask me all the data required for the liquid calculation. Of course, if I will click only the diameter, we will require less data. But for your case, we will need also, I will click the gas mass transfer, and the software will start to ask me all the data. The first is the diffusivity. If you know the molecular diffusivity, good. It's not when you click 0 by the molecular weight of the solvent and the gas and the temperature in internal models we have inside, we're able to calculate. The model diffusivity is very known and simple to know. Now, this is very important. It is the gas solubility. We need to know what is the gas solubility because it is the driving force that we use in order to transfer our mass from the liquid, from the gas to the liquid. The order of magnitude of the solubility of gas, oxygen, is around 1 per cubic meter. And the concentration, if we click, for instance, 0.2, I will know what will be the gas rate under this concentration when the concentration of the gas in the liquid phase will be 0.2. If I want to know the maximum capability of my equipment to transfer, we click 0 here. And this is the maximum. More than this, we will not be able to transfer. And it is very important number because this will be the maximum you will be able. So more than this, the process will be not so effective. And you are feeling it when you start to have high rate of growing, how you need to provide more oxygen, you need to increase the velocity, but there is a point that it's not possible to do more. So take care, because if you are expecting to have more, you will be very fast going to the stationary stage and more to the depth state that nobody can want to be there. So we click OK, and now we need the flow we enter. If you click here, a big number will be the maximum one. And if you you see more than this will be floating. So I will use, for instance, 1 is some let's say 1.4. This is the middle of the way, okay, of this this equipment. And when you click OK, we need the surface tension because we're generating some drops. So let's say I will use 0.07. And once you click OK, you see, oh, significant non-uniformity of gas spectrum. So we are not using all the time. And when you click OK, the software gives me that we have this is the kilogram per hour in the maximum capability of my tank. But we can calculate more. So let's do it from the beginning. We know what the diameter of the tank you see is about 433 micron, or we have the gas holdup, it's about 25%, it's very high here, it's very good in this equipment. We can calculate the mass transfer coefficient, 0.14, not so high, not so low, it's in the middle of the way. As you see, all the parameters are ready to use with no problem. Now, let's say I want to see all of them. I want to go to scale up. Let's say I'm happy with this and I want to reproduce exactly the same in a big equipment. The guideline for you, if you are in the industry, and maybe you, yes, but maybe no, maybe you are not so familiar for many important mixing parameters that are controlling the process, this button will be very helpful. Because in this button, you are bringing the data from the 1 liter. You can ask, okay, I have 6,000 liter equipment, by geometry similarity, we will calculate what is the diameter, the order of magnitude of the diameter that we'll able to you will find in the big scale. And if you ask the software about to have the same mass transfer rate in the gas liquid, the software will tell you exactly what is the velocity you need to apply in this big equipment which parameter is controlling this specific mass transfer. In our case, it's a energy of dissipation rate. So you see the energy dissipation rate is similar, and the other parameter will be a little different. Take care about it. For instance, this mixing tank can generate impurities. If your material will have another reaction that happening there, you are taking one order of magnitude more, so take care of it. Once we click OK, the software is providing the best prototype, and when we click Save, we have now our big equipment, exactly the same geometry for big equipment, and we can calculate, for instance, the mass transfer coefficient, okay, for 230 cube per hour. That is the same, and you see this exactly the same or very, very similar. Okay, this is very similar. Now, you can tell me, okay, but my equipment is not exactly the same geometry. Of course, it's the best prototype. Let's go and now, once we have a model, approximate to my real life. So you click clone, you have option number 1, and the option number 1, let's change. Let's change, for instance, the tank. The tank will be, for instance, 2,000, okay, instead 1,000. And you want to use 5,300 liters, okay? And you have 4 buffers like this is okay, and you have this turbine. You have the diameter will be 350 and 450, and here will be 125 and 150. Okay, this is the distance between this will be, let's say, 800. Okay. So the distance, sorry, not the diameter, 450. Sorry, this is my mistake. The distance between the equipment will be 800. Okay, like this. And when we click OK, this is my real life, and can calculate directly what happened with the mass transfer coefficient when we have the same 230 I did before that. Okay, and once we click OK, you see that, oh, in this case, it's not so good. And now you can compare between them, and you can run and change that I did before that. For instance, my velocity was 100. I can go to 150 because I think I have enough power for it. And now changing it, oh, now it's 0.7 or 0.3. And if you want to compare between them, you click process analysis, and you bring the gas transfer dispersion, and the software will provide to you in one table all the results in the real life, realistic ones, regarding the gas holdup, the mass transfer, the rate, okay? And you can see the difference between them. And if you can see all together, we can provide not only the gas, it's free for all the parameters, and here some other parameters that we know can influence your results. All of this you can export to Excel, and this part, of course, is simple. So this is that I wanted to show to you. We exactly live to our time. I will only cover some questions we have here. Okay. Why was energy of dissipation was used as scalar parameter rather than P divided by B or KLA? Or other? Yes, the answer is simple. Energy of dissipation is a fundamental mixing parameter, and it's power per volume but distributed in the tank. And sometimes the average will be the same one for different kinds of equipment, even if the equipment is more shear rate, is more shear than pumping. And the shear in this case, you know, is very important. So this is the reason that we talk about mixing parameters. And after that, of course, if you calculate the KLA, yes, a consequence of the power per volume or energy of dissipation will, or shear rate, will be the KLA. The KLA is a function of it. Okay? So in this way, you can connect between them. But the guideline is something we have not enough knowledge. We don't know the parameters, all the parameters we need in order to calculate the KLA. You can be guided by the pure hydrodynamic parameters, emancipation, shear rate, circulation flow, all of them you can use, as I will show in the presentation. based in the Hovion example. How is different VisiMix from ANSYS and Fluent? The answer is simple. In VisiMix, we are coming with some semi-empirical model, and we are bringing the model is included intrinsic all the characterization of different kinds of flow that will be able to generate, and it is a model dedicated for mixing. All the coefficients we are using are not general and using for the geometry. It was this parameter were defined for mixing studies. We'll get slides of this. Yes, of course you will get. We'll upload in our website the presentation, the video, and the explanation that we are providing to you now. Does your program provide the radial actual temperature profile versus time? Yes, we are providing the temperature as a function of the time. When we have endotherm of exotherm, if you have it, we will be able to provide. It will be a temperature as a function of the time. Regarding in different points in the tank, it should be very, very high heat release in order to detect some locally heating hotspots. It can happen, and we are developing for this in the pipe of chemical flow chemistry. We are developing this, and you will find it. It is typical when it is in the static mixer, but when we will come to the stirred tank, some of the capability to distribute this hotspot is efficient, so it is not so common. Of course, we can discuss about it. Do you support only for mixing equipment, only the complete fermenter design? The software is providing exactly that I showed to you. There are here some parameters that will help in order to design the complete fermenter. But of course, the scientific part is not covered. So we are not expect about the microorganism you will use. This is not our one. Once you know it, we will be able, of course, you will be able to take in consideration the mixing parameter I showed to you in order to progress with the fermentation. Do you support? Okay, and we have here in Hebrew where we talk about the diffusers. Yes, the diffusers we need mainly to understand that the diffuser, the main action is to introduce the gas to the medium. So if we calculate, if we know what is the velocity around the place of the spargel, and we know that the spargel is located in the bottom of the tank, and we take in consideration it in the flow pattern that we'll be able to calculate, and we take in consideration the static pressure, so how much material you have in the tank, you need only to pass this pressure, and not once the gas is entering there, the mixing is controlling the mass transfer and more. If we're in the limit situation, maybe this will be important in the most of the cases. Once you know that the gas is able to enter, the mixing is controlling the mass transfer. How do we learn the pricing? Okay, the pricing will contact you separate. Normally the pricing at the starting point, and after that is really depending on how we are progressing, okay? How we are progressing with the company, what are your capabilities, which kinds of model we use, and how many people you will want to use. All of this we take in consideration, of course, at the beginning of the way. It will include a complete training, basic training, follow-up projects to be sure that you feed the data and get good results, or results that are representative, maybe not so good, but are representative, yes. And to get some conclusions to the next. So it was a pleasure for me to be with you again. We are over in 5 minutes. And we'd like to see you more in more mixing presentations about different unit operations that are coming. We have our next meeting around a month and a half. We will, of course, provide some advertise about it. about the unit operation we'll use, or if we are exactly in the time that we'll release a new software. So maybe we will have some explanation about what is the new software we'll release. And it will be really a very interesting and scientific progress regarding to the connection between the mixing and the reactions in the realistic environment. Thank you very much for all. A pleasure to be with you. Come back and see you again in our next and future mixing forums. Bye-bye.